Okay, welcome back to Discrete Math. This is lesson 12. Today we're talking about random number generation. So this is some background information. This process that we're going to talk about is actually called pseudo-random number generation. That's not completely random because we have a sort of process to go about doing this. So it's not random by definition. What we do here is we use linear recurrences, which we just talked about, and modular arithmetic, was what we also just talked about, to make numbers. Now these recurrences take what's called a seed value, or the initial argument of the recurrence, just a place to start from. And this is the formal definition from Wikipedia. Have fun trying to decipher this. But what this is basically saying is that the function f, the function that we're using to generate these numbers, converges to the actual probability distribution. So f is going to converge to p given some epsilon greater than 0. And I should probably talk about the convergence formula eventually. I'll make a video about that later. Okay, so basic pseudo random number generator is going to take this form here. It's pretty fast to implement and run. It's going to take the form x of n is equal to a, where a is some integer, times x of n minus 1, which is going to be the previous term, plus c, some other integer. And this is all going to be done mod m. As you can see, we have chosen a and c to be some integer modulo m. And also we have some initial condition x naught, which is also mod m. And we have to choose our c carefully so that the GCD of c and m is 1. Okay, so this will generate random numbers between 0 and m, minus 1. So here's some sample calculations. We have that x naught is 3, and we have that x of n is going to be 5 times x of n minus 1 plus 4 mod 23. And notice that I chose 23 because it's prime, and it's easy to find coprime numbers with 23 prime number. So here's the sequence that's generated. As you can see, it looks pretty random. And here's some Java code that I included. Pretty straightforward. So we have our base case here. If n is 0, then we return 3. Otherwise, we return a1, or a, which is 5, times x of n minus 1, which we just called gen here, and of n minus 1, plus 4, which is our constant. And then we have our modulus here. That's all we have to do. Okay, so here's some applications of this. Many programming languages have built-in random number generators, and they tend to use the computer's time, or the time since like 1970, as a seed. So it takes the same form that we just talked about. For a few ways that people have implemented this is that Microsoft's Visual C++ compiler uses m to be 2 to the 32, because 32 bits in their operating system for the earlier versions of Windows. C to be 1, just convenient, I guess, and a to be this number right here. Another example of this would be Java's random utility package, and that includes an m of 2 to the 48, and c of 11, and a to be this guy right here. So as you can see, this technique is pretty commonly used to generate random numbers in a fairly uniform distribution. That's about it. Thanks for watching. Wait, there's more. We can transform these generations. If let's say that we want to generate a real number, or if we want to generate some sort of sequence between two integers. Well, if we have a generator G that generates numbers from 0 to k minus 1 using this method, we can get a number between 0 and 1, right, just by dividing by k. And it works best with large values of k, otherwise we can have patterns or obvious things emerge. So if we want a number between 3 and k minus 2, well, we can just add 3 to g after we apply g. And if we want a real number between 0 and m, we can divide g by k, and multiply this result by m. That's the basic idea of transforming it. You can also do other things like adding them, which will affect the variances and so on. That's the basic information. So this is really it. Thanks for watching. See you next time.